still coming. It's kind of. Yes, good to see you. It's kind of.
For the first three talks, there's
no learning, right?
What's the other track? The other tracks are on object recognition.
Yeah, it's human. Okay. I think we could start it. Okay, good morning again. I believe we are ready to start. People are sort of here. So my name is Tomáš Pajdla. I'm chairing this session together with Torsten Sattler, and Torsten will introduce the first speaker.
Yes. Could also the spotlight presenters please come to the front, their designated seats. Thank you. Okay, so the first paper in the session is Rotation Averaging and Strong Duality by Anders Eriksson, Kahl Olsson, Fredrik Kahl, and Tat-Jun, and Anders will present the paper.
Thank you. Right. So in this work, we explore the role of duality principles within the problem of rotation averaging. A fundamental problem in 3D reconstruction is determining how the cameras were oriented. And rotation averaging typically appears as a core subproblem in such structure for motion pipelines. It's defined as the task of finding the absolute rotations of a set of cameras, given estimates of relative rotations between the cameras. In the absence of noise, you can find absolute rotations, here denoted Ri and Rj, that are completely consistent with all the given relative rotations, Rij. However, in the presence of noise, a solution to these inequalities is not guaranteed to exist. Instead, it is typically solved in a least metric sense, here for some p greater than 1 and some distance function d. A number of distinct choices of metrics on rotations exist, but in this work, we restrict ourselves to the caudal distance. This is a common choice that has also proven to be very convenient one, as it is quadratic in its entries, leading to a particularly simple derivation and form of the associated dual problem. It's simply defined as the Euclidean distance in the embedding space of 3x3 matrices. So this is our primal problem, the rotation averaging problem we wish to solve. So note that this is a non-convex problem caused by the rotational constraints, making it difficult to solve with guarantees on global optimality. If you introduce some additional notation, we can simplify our problem in the following way. Here R tilde is a matrix containing the given relative rotations with zeros where such measurements are missing. We also introduce lambda, a diagonal matrix with the Lagrangian multipliers or dual variables along the diagonal. From this primal problem, we will now derive the associated dual problem. And for the sake of simplicity, I will, for this presentation, relax the rotation constraints to orthogonality constraints. I'll refer you to our paper for more technical details. So deriving the dual problem is done in the usual way. We first express the Lagrangian as the following function in R and lambda. It's obtained as a sum of the objective function and the constraints, weighted by the Lagrangian multipliers lambda. The dual problem is then defined as the following max-min formulation of the Lagrangian, first in R and then in lambda. It turns out that here, this problem is particularly simple. This follows since the unrestricted optimum of the inner minimization in R is either minus the trace of lambda or minus infinity, if lambda minus R tilde is positive semi-definite, or minus infinity otherwise. From this, we can write the dual problem as shown on the bottom here. So that gives us these two problems. Our original primal problem in blue, that's the rotation averaging problem we are interested in solving. And then in green, the associated and maybe somewhat abstract dual problem we just derived. Our primal problem is, as mentioned earlier, a non-convex problem which is in general difficult to solve globally. Our dual problem, on the other hand, is a convex problem. It's the maximization of a linear objective with a positive semi-definite cone constraint. This is not by chance. In fact, it can be shown that the dual problem will always be convex, regardless of the primal being convex or not. Also by construction, the dual problem will always be an underestimator of the primal problem. This is a property known as weak duality. Sometimes it happens that this equality is tight, that P equals D. Then we say that strong duality holds. And this can be shown to hold if the primal problem is convex. However, it typically does not hold if the primal is non-convex, with a handful of notable exceptions. So why is this important? Well, if we can establish that strong duality holds between our primal and dual problems, it means that they are in some sense equivalent. Since they have the same optima, we can consequently solve our original and difficult non-convex problem by instead solving the associated convex and simple dual problem. That is, it allows us to obtain certifiably global solutions to a class of important non-convex problems very efficiently. So the question is then, does strong duality hold for rotation averaging? Well, it has been observed that quite often it does indeed hold, especially if the noise levels aren't too severe. And the motivation for this work was based on this observation. The two questions we wanted to answer were, can we say more about when this happens? And how do you then solve the resulting dual problem efficiently? So this then leads us to the two main contributions made in this work. First, we established sufficient conditions with theoretical bounds for strong duality to hold. And second, we propose a scalable algorithm for efficiently solving the resulting dual problem. Off-the-shelf semi-definite program solvers typically don't scale very well. The proofs of these results are somewhat lengthy, so I will not go into them here. But if you're interested, I'll refer you to the paper or to stop by our poster later today. I'll instead just move ahead to the main results. The first of which is the following theorem. What this theorem provides are sufficient conditions for strong duality to hold for the problem of rotation averaging. And what it essentially says is this, that if your problem permits a solution where the angular residual is less than alpha max, then strong duality will hold. Note that this expression only involves quantities related to the visibility matrix or camera graph of the problem at hand, all known beforehand. So this bound will consequently be different depending on the problem instance. But for a fully connected camera graph, this bound will lie between about 43 and 60 degrees, depending on the total number of cameras, which is quite a generous bound. It should also be noted that this bound is always strictly positive, which means that it also says that strong duality will hold for any rotation averaging problem as long as the noise levels are sufficiently small. The second contribution made is a simple and scalable algorithm for efficiently solving the dual problem. Well, we don't actually solve the dual problem. Instead, we solve the dual of the dual. But since they're both convex, they can be considered equivalent. The dual of the dual can be written as follows. A linear objective function with a semi-definite cone and constant diagonal constraints. Note that this is a block matrix where each of the entries denote 3x3 matrices. And our algorithm is then based on the observation that if we fix all but the first row and column, the problem has a closed form solution, given on the right. Here note that the matrix square root and inversion in this expression only involves 3x3 matrices, so it can be consequently be evaluated very efficiently. So our proposed algorithm then simply proceeds by looping sequentially over which row and column is updated until convergence. So I'll finish off by showing some experimental results. First, we have a sequence of 133 images of a water tower at Alcatraz prison. Here, the resulting largest angular residual is just under 8 degrees, well below the, in this instance, 43 degrees required by our main theorem. And our proposed algorithm solves the dual problem in about 13 seconds. And this is implemented in MATLAB, by the way, compared to Sedumi, which is an off-the-shelf convex solver, which takes about 2 minutes. So we're about 10 times faster. Next, we have about 300 images of the giant Buddha statue in Hong Kong. Here, the largest angular residual is about 7 degrees. The bound provided by our main theorem in this instance is about 14 degrees, so a bit lower than in the previous case, but still more than sufficiently large to guarantee strong duality. And our proposed algorithm here is about 100 times faster than Sedumi. However, there are instances when our bound does not quite suffice. In this image sequence, the largest residual is 8.6 degrees, but the bound provided by our main theorem is only 3.6. However, as it turns out, strong duality still holds in this case, but it's not guaranteed by our theorem. So there's still work to be done here. We should be able to strengthen these bounds even further. Still, our proposed algorithm outperforms Sedumi here by a factor of about 70. So, in conclusion, we have shown that rotation averaging can be solved with guarantees on global optimality through its dual formulation, as long as the noise levels are not too high. We proposed a method for efficiently solving the dual problem for large-scale instances, but there is still room for improvement. Empirically, we've observed that strong duality occurs for residual errors much greater than predicted by the main theorem of this paper. Thank you for your time, and please come to our poster session.
Okay, thank you very much. Questions? Okay, please come to the mic, which is over there. The closest mic is over there.
Hello. So, is there a definition of the sort of high noise, low noise in this case?
Sorry.
Can you say it again, please?
So, what can be defined as a high noise, low noise in this case?
Yeah, that's a good question. Our bounds are defined on the resulting angular residuals, so we haven't established the connection between the actual input noise levels and the residuals yet, but we're working on it.
Thank you.
Can you hear me? So the question really is with the chordal distance that you're defining, right? That's in a least square sense, and then you're looking at the gap between the primal and the dual. But how do you deal with large-scale outliers? Because if you have large data sets, like these are relatively much smaller data sets than what, say, your standard things that one can solve with gradient descent on Lie groups, for example, right? So in general, we have found that you tend to have some outliers which are completely wrong. So then I don't know if your bounds are going to hold in that case.
No, we don't really address outliers in this work.
So you would still need some, for this to be really viable as a real optimization scheme, you would need some way of filtering out outliers, I suppose.
Yes, I suppose. I still think you can still say something. If you have a case with outliers, what will probably happen...
Outliers can be very large. So.
Sorry?
Outliers can be very large.
Yes. What will happen then, strong duality will not hold, and that will tell you something about the problem, that you probably have outliers in it.
Okay.
And, yeah.
Okay, thank you very much. And let me invite the second speaker. Please, while he sets up, I will introduce the paper. Okay, we are back. So the next paper is Hybrid Camera Pose Estimation by Federico Camposeco, Andrea Cohen, Marc Pollefeys, and Torsten Sattler. And the talk will be given by Federico.
All right. Thank you very much. Can you hear me? Okay, so thank you all for being here. My name is Federico. This is joint work with Andrea, Marc Pollefeys, and Torsten Sattler. Our paper name is Hybrid Camera Pose Estimation, and it was funded by Google's Visual Positioning System in Zurich. Right, so as a brief reminder, let me start with what we mean by camera pose estimation for visual localization. So given an SFM model of an environment and its associated database images, the task of camera pose estimation is to find a 6-degree of freedom pose, in this case, of a query image with respect to this structure for motion model. Here, the query is shown in green and the database images, the query is shown in red and the database images are shown in green. This is a very important step for us to unlock applications in AR, VR, and also in mobile robotics. Now, the very classical and most common approach to finding the pose of the camera with respect to this model is by the use of 2D feature images and 3D points correspondences. This is known as 2D to 3D matches, and they provide each, in general, two algebraic constraints each. So if we have 3 of these, we can solve for the pose using the P3P solver. Now, advantages of this is that it's really, really fast. The execution of P3P is about 2 microseconds in modern computers. It only needs 3 matches, so the RANSAC procedure should terminate very, very quickly. However, the main disadvantage is that we need to have a good triangulation of our structure for motion points in order to get a good pose to begin with. A more recent approach to finding the pose of the camera is to only rely in 2D to 2D matches between the query image and the database images. Now, each of these, known as 2D to 2D matches, only provide 1 algebraic constraint each. Thus, we need to have 6 of these in order to get a full 6-degree of freedom pose. This is known as a 6-point solver in our work, and it has been proposed in ICCV 2015. Advantages of this is that more matches are possible between the query image and the database images, mainly because we don't need to have triangulated observations in the database images for us to be able to draw matches between query and database. Of course, because of this, it's not affected by any bad triangulation. We're not anymore looking at the point cloud in the SFM model, we're just looking at the database images. The main disadvantage is in runtime. It is really, really slow. The solver itself is about 1,000 times slower than P3P, and since we also need to sample 6 points in order to get a solution, the RANSAC iterations will be much larger. So the trade-off between the 2D to 2D and 2D to 3D solvers are, on one hand, if you only have 2D to 2D matches, you have a large runtime of your solver, but you have a very low sensitivity to bad 3D triangulated points, as I mentioned. On the other hand, if you have P3P, where you only rely on 2D to 3D matches, we will have a very small runtime of the solver, but you'll have very high sensitivity to 3D noise or 3D triangulation errors. So what we want to look at is solvers. Is it working? Do you have a projection? All right. Sorry. Yes, there we go. So what we want to look at is mixing matches between 2D to 3D and 2D to 2D in order to have a moderate runtime for our solvers and a moderate sensitivity to bad 3D triangulations. So we want to focus on 2 main questions. Sorry, this seems to be something wrong. You want to hold it for me? Or? Sorry. All right, yeah. So, okay, the first question we want to answer in this paper is this possible? And the second will be how to integrate this into a RANSAC scheme. All right, so the short answer to the first question is yes. Yes, we can have such solvers. We'll call them hybrid camera pose solvers. In this, okay, sorry. So it is simply a matter of finding a right combination of 2D to 2D and 2D to 3D matches in order to get the required 6-degree of freedom. So for the 6-DOF problem, we have thus 2 hybrid minimal problems that we can propose. The first combination would be having 4 2D to 2D matches and, 2 2D to 2D matches and 2 2D to 3D matches, called H22 in our formulation, and 4 2D to 2D matches and 1 2D to 3D matches, which we call H41. Right. So throughout this presentation, I'm only addressing the 6 degree of freedom camera pose estimation problem, as I mentioned. And for this, we have P3P, H22, H41, and the 6-point. So these are all the possible combinations of matches that we can have. However, we also extend this in our paper to camera problems where we know the vertical of the camera. This is a 4 degree of freedom problem, and we propose one new minimal solver. The problem of multi-camera query, where the scale of the query camera is not the same as the scale in the SFM model. And for this, we propose 3 more solvers. And finally, the problem of a known vertical multi-camera with a known scale query, for which we propose 3 new minimal solvers. Thus, in total, we have new 9 novel solvers that we propose in this paper. All right, so the procedure to generate or to get a minimal solution to each of these problems is similar for all of our combinations. So first, we take the 2D to 3D constraints and express the translation as a linear combination of the rotational parameters. Then we take the translation expression now that is a function of the rotational parameters R and expand the generalized epipolar constraints into polynomials in terms of the rotation parameters. We then take a Gromner basis generator and get minimal solvers for each of our 9 problems. So we synthetically validate our solvers by testing their numerical precision with noiseless data. And as you can see, they all perform well, and thus we can use them in real-world applications within RANSAC. As expected, the H41 and the H22 solvers have runtime which is in between the 6-point and the P3P solver. So we have this trade-off that we were talking about. Right, so at this point, we have at our disposal a minimal solver for each combination of matches that is possible for the 6 degree of freedom problem. So it is now time to answer the second question. How do we integrate this into RANSAC? Classical RANSAC deals with finding the in-layer set from a given single set of match types in a problem. So for example, in P3P, we will have only 2D to 3D matches, and then RANSAC is tasked with finding a set of in-layers from these matches, right? However, in our case, we have 2D to 2D matches and 2D to 3D matches, thus we must find a way to extend RANSAC in order to handle this multiplicity of matches. So the proposed H-RANSAC will find a set of in-layers from 2D to 3D matches and 2D to 2D matches. Right, so how does this roughly works? So at the beginning of each iteration of our RANSAC, we will sample a specific solver with probability PS. So instead of sampling a minimal set for a given minimal solver, we will first choose which problem to solve with the 2D to 2D matches and 2D to 3D matches that we have at our disposal. Thus, we will sample the probability S with the solver S with probability PS, which is given by the probability of sampling an all-in-layer set for solver S. Here, the probabilities involved here is the in-layer ratio of the 2D to 2D matches and the in-layer ratio of the 2D to 3D matches. Then we multiply this by the probability of not having seen an all-in-layer set by the kth iteration of solver S. Thus, the first term favors solvers that use matches with a high in-layer ratio and few matches, as with RANSAC. And the second term, however, counteracts the first, such that it is more exploratory to match combinations not used before, and we can have new combinations coming into our solver, and we are able to not get stuck in local minima. After we have chosen a solver, then we just go and sample the matches needed in order to solve this problem, as with RANSAC. So if we, for example, sample the H22 solver, we'll need to sample then 2 2D to 2D matches and 2 2D to 3D matches. Right. So we iterate like this, and when any of the number of iterations for each solver, Ks, exceeds the number of iterations, the termination criteria, uppercase Ks, we terminate H-RANSAC. This termination criteria is similar to the classical RANSAC, but the in-layer ratio is modified so that the in-layer ratio of both match sets is taken into account with a multiplicity for the solver in question. Right, so at this point we have our minimal solvers, we have our hybrid RANSAC, and we can try them on real data. As expected, we get more in-layers than simply using 2D to 2D or 2D to 3D matches. This might be obvious because we're simply using more data from the SFM to localize our image. This is good, of course, because if we have more in-layers, we can have a better refined pose, and that is good. But it's also very good because if we have more in-layers, we can better decide if the estimated pose is a good pose or if it's not. So this is the first way of estimating if a pose that we have the pose for is good or not. But what we can do better then is that we can decide if the estimated pose is good by the distribution of the inliers on the image. For example, in the image to your left, we see that we retrieved 2D to 3D inliers, which are in the foreground of the image. And this is because we have good 3D points in that part of the SFM, because the baseline the camera does well, and so on. However, we are also able to get inliers in the background of the image, where we were not able during the SFM procedure to get good 3D points because the baseline was very short. So we have a better distribution of our inliers, and we can better decide that this has been a pose that is correctly estimated. Also, as expected, we have better positional error and rotational error as compared to P3P and only using the 6 points within RANSAC, as shown by these CDFs. And the trade-off, as with the minimal solvers themselves, of the runtime of the full RANSAC procedure is also sitting somewhere in between using the pure solvers. So it is orders of magnitude faster than 6 points. However, there is some computational cost to be paid with respect to P3P if we want this increased accuracy and number of inliers. Also, we observe that our hybrid RANSAC scheme adapts differently to the types of images that we feed into it. So if we have, for example, an image that's very close to the query image that has good 3D triangulated points, our hybrid RANSAC will then guide the sampling of the solvers to mostly choose P3P and our hybrid solvers that have a high number of 2D to 3D matches required. On the other end, if we have a query image that mostly has objects that are very far from the query image, then the hybrid procedure will guide the sampling of the solvers to use 6 points more often, because, as I said before, we will mostly have points which are not well triangulated, seen in the image. And as before, as I mentioned, if we have a combination of both, we will sample uniformly with all our solvers. So to summarize, we have developed 9 novel hybrid minimal solvers, which mix 2D to 2D and 2D to 3D matches. We are targeting 4 different types of camera pose estimation problems. To handle this multiplicity of matches, we have introduced the H-RANSAC scheme that is able to handle diverse match types and also adapts to different types of images. Thank you very much. See you in posters C10 for your questions.
Thank you. And questions? No questions? Well, I have a question. Okay. So how do you parameterize rotations?
Right. So the parameterization of the rotation depends on the problem that we were solving. If we're solving the full 6-degree freedom problem, we parameterize using quaternions. But if we're solving, for example, an upright version of the problem where we do know the vertical, we parameterize using half-tangent parameterization. So we only have 4 parameters there, which have an internal nonlinear constraint, which is simpler. Yes.
So you have double solutions with quaternions. So what do you do with that?
Right. So that's an important point. Most of our minimal solvers are not very well optimized. The formulation is a very simple one. We just wanted to explore this multiplicity of matches in camera pose estimation. But I'm pretty sure that people can come up with better formulations for this solver to get better numerical precision and perhaps even less solutions that we have.
Thank you.
Okay, the last talk in this session is Certifiably Globally Optimal Solution to the Non-Minimal Relative Pose Problem by Jesus Briales, Laurent Kneip, Javier Gonzalez-Jimenez, and Jesus is going to give the talk.
Okay. Hi, everyone. Thank you for the introduction. It's a pleasure to be here to present this joint contribution with my colleagues, Laurent, Kneip, and Javier Gonzalez. So, whoops. Here. So, in this presentation, we will revisit a well-known classic and fundamental problem of computer vision. It is the relative pose problem for calibrated cameras. That is, given 3D points and observations of them from 2 calibrated cameras, find the corresponding relative orientation and translation up to scale between them. Whereas the gold standard for accuracy is to perform some kind of two-view bundle adjustment, this involves a high number of parameters due to their known points, and it's not trivial to initialize either. So, on the other hand, the well-known epipolar constraint, described by the essential metrics, depends only on 5 pose parameters, taking out the scale, and this has historically motivated using this constraint as an algebraic error in order to estimate the relative pose. The resulting problem is much lower dimensional, and in practice provide comparing results. So this is a classical problem, and a number of approaches have been proposed to solve it. The 8-point algorithm by Longet-Higgins, or its normalized version by Hartley, for example, rely on a linear relaxation of the existing constraints, and is thus suboptimal in general. Also, closed-form optimal solutions are given only for minimal cases, such as the case, for example, for the well-known 5-point case and the solution by Nister. And finally, different iterative approaches come without any optimality guarantees or rely on expensive branch and bound schemes. Overall, none of those approaches is able to solve the relative pose problem for more than minimal correspondences with certifiable optimality and in polynomial time. If we compare the solution provided by those approaches I mentioned to the optimal solution given by a global solver, the optimality gap in the objective may seem deceivingly small. However, checking the angular error between solutions reveals that errors may be quite large in the solution space, meaning that suboptimal approaches may miss the true solution and fall into local minima instead. So here in the figures, we show a box plot of error values for 500 evaluations each. So any non-zero error denotes a failure case for the method. We analyzed different parameters of the problem, such as the level of noise, the number of observations, field of view, or parallax, showing how these different parameters affect the inherent difficulty of the problem and push suboptimal approaches to fail more often. Also, evaluating on real data taken from the Thun dataset led to similar observations. And after all, this should not come as a big surprise, as even if simpler than bundle adjustment, the algebraic formulation is still a quite challenging optimization problem due to the different source of non-convexity we find in it. So this is a, I would say, quite non-convex problem. So after remarking the significance of this problem as a fundamental block for structure for motion, for example, and the shortfalls of currently existing methods, let me state the contribution of the present work. So we dealt with the non-convexity of the relative pose problem, building a convex relaxation that turns empirically tight, allowing us to develop an algorithm that can both recover and certify the optimal solution to this problem. For the rest of the presentation, I will basically show you the key steps that made this contribution possible. So, the relative pose problem may be written in many equivalent forms, and in particular, we start from this one in the slide, which comes from some previous work by Laurent Kneip. And if we write the constraints explicitly, this becomes a polynomial optimization problem, which we know we can write as equivalently as a quadratically constrained quadratic program by introducing an appropriate intermediate variable x. This choice is not random, by the way, as it will be critical for subsequent steps. Now, for this kind of problem, a classical relaxation is Chor's relaxation, which provides a convex semi-definite program. When applying a relaxation, as some colleague mentioned before in the first talk, our best hope is that it is tight. That is, that the optimal objectives remain the same both for the original problem and the new relaxation. However, this relaxation we have here is not tight for our problem as we currently formulated it. So a second key insight becomes fundamental for the success of our approach. It is well known in the optimization community that adding redundant, linearly independent constraints to the original problem may improve the tightness of the relaxation, as these additional constraints shrink the relaxation domain. You will see this in a moment. So luckily, there is plenty of redundant constraints to leverage in our problem. So in our previous CVPR work, we found out that for a whole family of quadratic problems involving a 3D rotation, there exists a redundant characterization of the rotation constraints that makes short relaxation empirically tight, providing a certifiable global convex solver for those problems. Here, we tried them, again, with all those constraints, adding them to our problem. However, this was not enough to make the relaxation tight in the present case. So we turned towards two other tricks for producing additional constraints, which, as I said, are fundamental for the relaxation scheme. The first is to multiply the original rotation and unit constraints times elements of the rotation or translation to get this way cubic and quartic constraints that we can make quadratic again, which is an important feature because we have a quadratically constrained quadratic product in the relaxation. So we use the elements in the auxiliary variable x to produce more quadratic constraints from the cubic and quartic. And secondly, we use the original constraint on this auxiliary variable x that has rank equal 1 to produce yet more quadratic constraints from 2 by 2 determinants. In the figure, you can see, for example, some examples of these 2 by 2 determinants from the existing 270 permutations. So this way, we end up with several hundred of additional constraints, which can be still handled by any of the shared solver. Well, and at this point, now yes, we are using all these constraints I just presented, we are in a position where the semi-definite relaxation is actually tight. And we are left then with the ultimate question. Given this tight relaxation, are we able to recover the optimal solution to the original problem from the solution to the convex relaxation, which we know how to solve globally? Well, for Chor's relaxation, it is a classic result that if the rank of the primal SDP solution is 1, we can recover the original solution to the original problem from its low rank decomposition. However, in our case, another challenge is that the solution of the tight primal semi-definite problem has rank 4. And this is proof in our paper as the original problem has 4 global solutions if well defined. And this is an effect of the symmetries that exist in the algebraic cost for the epipolar constraint. As a result, we also show that the corresponding primal SDP relaxation, if tight, has an infinite set of solutions that form a convex hull of solutions with rank going from 1 to 4. In practice, when using a typical interior point method to solve the semi-definite problem, the use of log barriers promotes that we get one of those interior solutions, which has rank 4. So overall, this makes recovering the solution not as straightforward as in the classic rank 1 case. Yet, through some empirical observations involving multiplicity and structure of the eigenvalue decomposition for this rank 4 solution we obtained, we were able to produce an algorithm that recovers all the underlying solutions to the original problem. And that covers all the ingredients, indeed, required to develop an algorithm that provides a certifiable global solution to this problem. In a nutshell, the steps are: given the problem data, build the SDP relaxation with all the proposed constraints. And that actually means compute the data metrics because the constraints are all fixed and all the same for any problem. Then solve this convex semi-definite problem, both in the primal and dual forms. Compute the non-zero eigenspace of the primal SDP solution, which we expect to be rank 4, so it's a small computation. Then recover the candidate solution to the original problem from this eigenspace using the heuristic procedure we cover in the paper. And finally, check the optimality of this candidate we obtained using the dual semi-definite solution as an optimality certificate. If the optimality is not certified, that would mean that some assumption we made didn't hold. For example, the tightness could be failing as an assumption. But the interesting thing is that in practice, all the non-degenerate problems we tried would be correctly certified as optimal. So the tightness assumption would hold. And this brings us back to our earlier results, where the displayed global solver is, in fact, the same approach we just presented. So the results show how, indeed, for all tested cases, which were quite a few, we were able to certify the optimality of our solution, which resulted to have a numerically zero optimality gap, proving, by the way, that the other approaches were suboptimal in many cases. So, to sum up, there are several interesting lessons learned from this work. First, traditional solvers may perform poorly in the relative pose problem, leading to suboptimal solutions. And despite the importance of this problem, a global polynomial time non-minimal solver has been missing so far. Here, we developed such an empirical global solver based on a convex semi-definite relaxation, and on the process, we highlighted two interesting technical points. One was that the use of redundant constraints to deal with fundamental constraints of geometric computer vision, such as 3D rotations, is a pretty powerful tool. And the other was an example on how to undo semi-definite relaxations in the non-trivial scenarios where the original problem has multiple solutions. So overall, we find the fact that the proposed convex relaxation holds tight in every case highly surprising, is empirical, but yet we are very excited about the generalizations and applications this work may have in other estimation and optimization problems of computer vision. So thank you very much for your attention, and feel welcome to come and discuss all the details of this approach in the upcoming poster session in C13. Thank you.
Thank you very much for the nice talk. Are there questions?
Too hard.
Okay, I have a question. What about runtime? How long does it take to compute the solution?
Yeah, sure. So that's an important question because actually this is building on semi-definite solvers, which takes some time. It's not like 1 microsecond. It takes below 1 second for sure, and actually it's rather a theoretical contribution right now. I know that from the structure of the problem, you can build customized solvers for this kind of problem, which can go way faster. So it's still much faster than any branch and bound, so below 1 second, and with potential for improvement in the future.
Do you have a rough idea of how much you can improve it in runtime?
Let me see. Actually, my prior experience, I cannot assert anything here, but my prior experience with different problems where we did similar tricks, for example, in post-graph optimization, we end up with a way to do it as fast as any Gauss-Newton solver while retaining the global optimality guarantees. So that's the top. You can actually, with a little lag, you can make it as fast as any iterative solver and still being global.
Are there any other questions? If not, let's thank the speaker. And next we are going to have the spotlights. But before we start with spotlights, let's thank all three speakers again. If the first spotlight presenter could already come up.
Good morning, everyone. I'm Yuelo. I'm glad to here to present our single wheel stair matching. This is the drawn wall with Jimmy Ren, Mude Lin, Jiahao Pang, Wenxiu Sun, Hongsheng Li, and Liang Lin. Monocular depth estimation is the task that, given an image, the absolute distance from the object to the camera space are predicting on all the pixels. Previous method relies on directly regressing the depth values, but those methods require a large amount of accurately labeled dense maps, which are hard to obtain in reality. Recently, some unsupervised and semi-supervised methods were proposed. They instead supervise on the reconstructed image from a stereo pair rather than the depth map. However, during inference, no explicit geometric constraint were imposed in the model itself, resulting in a low interpretability and a suboptimal result. Spatial transformation network brings a new idea that if we impose the transformation explicitly in the model itself, it may be able to make better inference on the task due to the imposed geometric constraints. We are also inspired by the fact that predicting depth from stereo image generally have higher accuracy than from a single image. Research have shown that the model trained on computer synthesized data have good generalization ability on real-world data, since stereo matching is only about finding the similar pixels. This motivates us to directly reform the simple deep models by adding explicit spatial transformations and turning this monocular depth estimation problem into a stereo matching way. It will reduce expensive data use and promote model capacity. Here comes to our approach. We show for the first time that monocular depth estimation problem can be reformulated as a stereo matching problem in which the right wheel is automatically generated by a high-quality wheel synthesis network. It presents some key insights. It explicitly models the transformation in the model and imposes strong geometric constraints. It reduces the demand of expensive wheel depth data, and it improves generalization ability. And our pipeline can be collectively trained in an end-to-end fashion that optimizes the overall performance. Here is the detail. First stage is wheel synthesis. We basically adopt the D3D model to predict the probabilistic disparity map to reconstruct a high-quality right image. Second stage is stereo matching, and we adopt the popular DisperNet C structure as the design model. Both models can be trained on an inexpensive data resource, and following up end-to-end fine-tuning optimize the full pipeline. Moreover, by explicitly modeling the geometric transformation and enforcing geometric constraints, like the pixel movement in the selection module and the 1D correlation in DisperNet, we achieve better performance and interpretability of the model during inference. Here are the quantitative results. We can see from the table that almost all evaluation metrics are improved over the previous methods. The absolute relative difference, namely ARD, is reduced by 16%. Qualitative evaluation on KT is also provided here. We can see that our model produces more accurate and visually appealing results as well compared to the current state-of-the-art methods. Those results show the good generalization ability of our model, which was trained on KT only, but was evaluated on other scenes. From the right, you can see that even though the scenes are quite different from those in KT, our model is still able to make reasonable inference on the unseen geometry. We also present the comparison between our method and a traditional stereometric method. And the table indicates that our method is the first monocular depth estimation method that can surpass the traditional block matching methods. Thanks for listening and welcome to our poster session.
Hello, my name is Björn Hefner, and this is a joint work with Ivar Keogh, Thomas Möllenhoff, and Daniel Kremers. We present a novel variational approach to jointly solve the two well-known problems of single depth map super resolution and shape from shading. Emergence of cheap commodity RGB-D sensors opened many doors and new possibilities in the area of 3D reconstruction. Yet, the delivered depth map misses fine geometric details due to noise, quantization effects, and, more importantly, the coarse resolution of the depth. Thus, depth super resolution is a well-known problem, and countless ways to tackle it have been proposed. Our work targets the ill-posed problem of single depth map super resolution, and is resolved using the shading information in the companion RGB image. This brings us to shape from shading. It relates a single image I with an image formation model R and tries to solve for the related depth map Z, given the lighting L and the surface reflectance rho. shape from shading is an ill-posed problem, and its complexity can be nicely visualized using the workshop metaphor. As a single image can be explained by a flat shape illuminated uniformly but painted in a complex manner, by a white and frontally lit surface with a complex geometry, or by a white planar surface illuminated in a complex manner. In view of this brief discussion on single depth map super resolution and shape from shading, we propose to fight ill-posedness with ill-posedness to jointly solve the depth super resolution and shape from shading. The low frequency information necessary to disambiguate shape from shading could be conveyed by the geometric data. Similarly, the high frequency information necessary to achieve detail preserving depth super resolution could be provided by the photometric data. Using the spherical harmonics approximation for the image formation model R, the image I can be described as the product of the albedo rho with the scalar product between the light vector L and the surface normals N. With a pinhole camera model, the surface normals N can be written in closed form with respect to Z, the focal length F, and the pixel coordinates with respect to the principal point. This leads to the final variational formulation with two additional prior terms, namely P1, regularizing Z in a minimal surface manner, and P2, inferring a piecewise constant albedo rho. To make this nonlinear optimization with respect to the depth maps tractable, an auxiliary variable theta is introduced to separate the difficulty induced by the nonlinearity from that induced by the dependency on the gradient. This resulting non-convex, non-smooth optimization problem is solved using a multi-block variant of ADMM. Thanks to our variational formulation, we are able to recover high-resolution depth maps with fine scale details from a single RGB-D frame, as can be seen in these challenging real-world examples. Our method nicely separates the depth from the albedo and gives superior results for both. Wherever color is saturated, the minimal surface prior drives the depth into a meaningful minimum. Even when the reflectance is oversegmented, the depth estimate does not seem to deteriorate, and still, fine scale details like the wrinkles of the trousers are nicely visible. We also compared our method against multi-view approaches and are still able to be on par, although our approach needs significantly less data. Also, on challenging datasets with more complex lighting, our single-view approach can result in high-resolution depth maps with fine-scale details compared to other multi-view approaches. Thank you for your attention. The code will be uploaded online, and please visit us at our poster with the number C19.
Hello, everyone. My name is Tat-Jun from Princeton Vision and Robotics Group. I'm here to briefly introduce a paper with my advisor, Professor Tan van Hauser, about deep depth completion of a single RGB-D image. These days, RGB-D sensors have become widely available and are enabling many future applications. However, if you look at the RGB-D image from the sensor, the color image are beautiful as usual, but the depth image often have a lot of missing data as shown in white here. This happens whether for bright illumination, distant surfaces, shining surfaces, thin structures, and black surfaces. And in this work, our goal is to complete the depth image from the sensor with the help of a well-aligned color image. And of course, there are previous work addressing this problem, such as drawing bilateral filtering or using deep neural network. However, they either work only for small holes or designed for depth estimation from only color image. In this work, we really wish to complete the depth image with a large hole. And of course, an obvious approach is to feed the color and sensor depths directly into a neural network and regress the complete depths. However, this approach doesn't work well, since estimating absolute depths require a combination of local feature and global context. Instead, we start from the color image only and train the fully convolutional neural network to estimate the surface normal map. We then feed the estimated surface normal together with the sensor depths into a global linear optimization to solve for the complete depths. But why do we estimate the surface normal in the middle? Two reasons. First of all, estimating local surface normal is easier than estimating depths directly. Surface normal are constant for pixels within the planar region and are mostly determined by local textural shading. There are also unit vectors ranging from -1 to 1, which are numerically easier to regress than arbitrary values, such as absolute depth value. Second, solving for depth from normal can integrate surface constraint for the entire thing globally. Although the equations for integrating normals are nonlinear and can be under constraint, we linearize them and provide regularization from the sensor depths to achieve an efficient, robust, and global solution. Of course, we had to address many questions in implementing our approach. I will skip these as time is limited here, and please check our poster for the answers to these questions. Now let's look at the results. First, here are some qualitative results with the color and sensor depths as input and our completed depths output, and the 3D visualization of the input and output point cloud. And in this last example, please notice that the chair on the left was correctly reconstructed, even though it was completely missing from this sensor depths. And quantitatively, we compare to other depth completion method and achieve best performance. And to the extreme case, we run our method using only 1 pixel of depth for the global scale and still outperform other depth estimation method under the same setting. And here, an interesting question to ask is how much depth do we actually need in order to get a high-quality dense depth? To answer this, we run our method with depth sampled from different number of pixels. Apparently, having more depth samples keeps improving the results, but not really much after 100. And on average, using 100 depth samples, our method generates dense depths with 70% of pixel error controlled within 5% of the depths. A further study is required to understand the impact of this finding on the design of future depth sensor. All right, thank you for your attention, and code and dataset are all available online. Please check our project webpage or scan the QR code, and also please come to our poster for more details, especially if you want to know the answer to those questions. Thank you.
Hello, Laurent. In this work, we propose multi-view harmonized bilinear network for 3D object recognition. And my name is Tan Yu. I'm from NTU, Singapore. This is joint work with Professor Meng Jingjing and Professor Wenxiu Song from Sunny Buffalo. This is overview of our network. Given a 3D object, we project it into multiple different views. And for each view, we input it into a very simple 2D CNN and get its convolutional feature map. After that, we pull all the local convolutional features of all the convolutional feature maps into one global representation. So the proposed harmonized bilinear network. Actually, our proposed harmonized bilinear network is an improved version of original bilinear pooling. And we will see that the harmonizing operation can significantly boost the recognition performance of the network. The existing method has some drawbacks. For example, given two 3D objects, object A and object B, the similarity scores between these two objects using MVCN will be equivalent to the sum of similarity score of all the possible matching pairs. However, not all the matching pairs are meaningful. So as shown in the red lines, the similarity score between non-corresponding views are not robust and may serve as noise. The gift improves this by only consider the corresponding views. In our method, we hope to hook up all the relevant patches and meanwhile decouple all the irrelevant patches. And since the out product is the explicit feature map or polynomial kernel, so we observe that the similarity score between two bilinear pooled features is equivalent to the output of the polynomial matching kernel. And using this polynomial matching kernel, we can automatically suppress the bad matchings and highlight good matchings. But the bilinear pooling still has the drawbacks. If we do SVD for the bilinear pooled features, we will see that the bilinear pooled feature will be equivalent to the weighted sum of the outer product of the eigenvalue vectors. However, and the weight is the eigenvalue value. However, the eigenvalues are changing significantly. It means that the first few eigenvalues are much larger than the rest of them. So the similarity score will be dominated by the first few very large single values. It's unbalanced. So our work is want to normalize this eigenvalue so that the total similarity score can be more balanced contributed by every component. And we use box cost transform to normalize this. And the box cost transform can be a generalized version of the square root normalization and logarithm normalization. And the lambda here is the parameter we can learn from our network in an end-to-end manner. And this is the very detailed architecture of our layer. And you can see there's two square root layer which aims to suppress the burstness, and the one by one collusion layer which is to suppress the overfitting. And we compare it with the other pooling method. We can see that without harmonizing, the original binary pooling can only achieve worse performance than sample pooling and mass pooling. We also compare with the existing method, and we achieve state-of-the-art on the two public datasets, ModelNet 10 and ModelNet 14. If you are interested in our work, please come to the poster session. Thank you.
Yeah, good morning. My name is Hao. I'm excited to bring here PPFNet Global Context-Aware Local Features for Robust 3D Point Matching. It is developed together with Tolga Biado and Torsten Illich from Technical University of Munich and Siemens Corporate Technology. Given two partially overlapped point clouds, the question is how to find local correspondences. It is an essential task in many applications like 3D reconstruction. One general solution is to use local descriptors to describe local geometries and match them in the feature space. Thus, how to formulate local features is critical. There are a lot of handcrafted features targeting this problem. They work well on clean 3D data, but when it comes to real data with low escalatory and missing parts, performances can be severely degenerated. Better results are obtained by data-driven deep learning methods like 3D Match and CGF. However, they both need to convert local patches into structured representation first. We propose PPFNet. It takes advantage of deep learning, but operates on sparse point-wise representation directly, which is more efficient. It incorporates point pair feature to increase robustness to rigid transformation, and it employs global context to make the learned features more powerful and discriminative for matching task. Given a local patch of point cloud, it is represented as a set of points with coordinate normal. Point pair features is computed for each point by pairing it with central reference point. As the distances and angles are preserved between every point pairs, PPF is variant under Euclidean transformation. In the inference stage, local patches are sampled, encoded, and fed into PointNet to get local features. A global feature which aggregates all the local information by max pooling operation is concatenated back to each of them. The combined features are further fused by multilayer perceptrons to form the final features. To guide the network to find appropriate feature pattern, supervision signal is important. 3D Match use samples of pair patches, CGF use triplets, but in both cases, only one elective sample is used. In our configuration, however, one patch from one fragment could be informed about all the patches from the other fragments. So we introduced tuple to fully utilize all the relationships. It is trying to minimize the feature distance between pairs while maintaining minimal margin with all the non-correspondent patches. The overall training pipeline of PPFNet includes all the previously mentioned components, and local patches are sampled from each of the fragment pairs to get their features by passing through PPFNet. An n-by-n feature distance matrix can be computed. On the other hand, based on the ground truth relative pose between fragments, we can compute the distance of the m patches in the original Euclidean space after alignment. By thresholding this distance matrix, we could get the ground truth pair and non-pair relationships, which is called correspondence matrix. With those two matrices, n-tuples could be computed and then guide the network for the training. Experimental results demonstrates the superior performance of PPFNet on correspondence matching and geometric registration. Thanks to PPFs, it is more tolerant to rotation. Due to its sparse representation, it's more robust to density variation. Also, it's fast and easy to compute. In conclusion, PPFNet is a deep learning framework for using global context for learning effective, efficient, and robust 3D local features from sparse point-wise representation. Thanks for your time. Please drop our poster for further discussion.
Hello, everyone. My name is Yaoqing Yang. This work was done together with Chen Feng, Yiru Shen, and Dong Tian at Mitsubishi Electric Research Labs. The work is called FoldingNet, inspired by the art of folding a paper to mimic different 3D object shapes. FoldingNet is a deep autoencoder that directly operates on point clouds. It provides an unsupervised way to extract code words from 3D point clouds for shape classification and generation. Our main contribution is to define the folding operation that deforms a 2D regular grid into a 3D shape through multi-layer perceptions. The reconstructed point cloud is compared with the input to drive the unsupervised training. The intuition behind FoldingNet is that 3D point clouds are often sampled from object surfaces, and we claim that any arbitrary object surfaces can be generated by folding an elastic paper using typical folding operations, such as fold, tear, stretch, and glue. What is the mathematical meaning of paper folding? It is essentially a mapping from the 2D space to the 3D space. By universal approximation theorem, we know that different MLPs can create different 3D shapes. In this paper, we further prove that a single MLP can approximate any 3D shape using a proper shape descriptor or the code word. What is the neural network actually doing when folding a paper? Here, we illustrate how the folding net deforms a regular 2D grid into the shape of a sofa. In the upper left image, we color-code the curvatures to visualize the folding lines in the 2D grid. In the bottom left image, we visualize large neighborhood distance by bright blue to show the cutting lines. The animation on the right shows the folding process from the fixed 2D grid into the sofa. It shows FoldingNet can indeed mimic a paper folding process. FoldingNet can automatically learn to paper fold more complicated 3D object shapes, such as this airplane. Okay. Note the 4 boundary lines of the paper grid are colored with red, yellow, blue, and green to highlight their 3D positions after folding. Here, we use the animation to demonstrate how the reconstructed 3D shapes evolve with more FoldingNet training iterations. As we can see, FoldingNet learns to fold better and better during training. We also show that FoldingNet code words are useful for shape interpolation. This is done by using FoldingNet decoder to reconstruct interpolated code words. This animation shows examples of both interclass and intraclass shape interpolation. Because 3D shape similarities often indicate semantic class similarities, and FoldingNet code words are learned by the shape similarity analysis. Thus, these code words contain a strong discriminative power for 3D object classification, even only using a linear classifier. This is shown in the table. Following the quantitative evaluation protocol from previous works, we obtained state-of-the-art linear SVM transfer classification accuracy on more than 40, which is even close to some cutting-edge supervised results. To summarize, FoldingNet realizes different paper folding operations for 3D unsupervised learning. It can even generate cuts and other sophisticated structures that are not isomorphic to a 2D plane. We show that FoldingNet code words automatically form clusters, enabling a better transfer classification. Finally, we would like to mention the next talk on AtlasNet, which highlights how several papers can be folded together with smaller shape reconstruction loss. Thank you very much. Please come to our poster at D9.
Hello, everyone. Sorry. Can you kill the sound, maybe? Just wait a second, please. Okay, I'll go on from here. Okay, I don't think I will speak on top of that because you won't understand anything, I guess. Okay. So in fact, our goal is to generate a mesh in this work. Sorry for the late start. From an input object on the left, we use existing methods to extract a latent vector and try to design a decoder to generate a mesh on the right. And we'll try this on an arbitrary shape, me. We build on point set gen work from last year and its point cloud representation. In its simplest form, the latent vector is fed to a multi-layered perceptron to output a fixed number of 3D points scattered in 3D on me. We built on this it is optimized by minimizing the chamfer distance against the ground truth point cloud. We build on this work by adding in the decoder architecture the prior that all generated points should belong to the same surface. In addition to the latent vector, our MLP takes as input the coordinates of a single 2D point sampled from a 2D patch and output the 3 coordinates of a single point. Now we're going to repeat this process and all the generated points will belong to the same surface. Furthermore, if we define the connectivity between samples in the patch, such as the triangulation of the points, for example, it can naturally be propagated to the 3D generated points and aligns with the generated surface. This type of decoder architecture generates a mesh without further post-processing. Interestingly, at inference time, by sampling the 2D patch more or less densely, we can generate as many points as we want. However, with this approach, reconstructing objects with complex topology such as me is hard with a single deformed patch. To solve this issue, instead of learning a single deformation, we learn K deformation to cover the generated object. And this works much better in practice. As you can see, I'm covered in papier-mâché. This actually goes back to the topological definition of a surface as being everywhere similar to a 2D patch, homeomorphic to R2. We show in the paper that, in fact, the representation we learn is an atlas. We show that this simple representation leads to better shape generation, improved generalization, and several free applications, such as single-view reconstruction here. From a single image on the left, we compare with voxels, octrees, and point cloud methods. Our result on the right outputs a surface representation. In the paper, we show many quantitative comparisons, as well as experiments on surface reconstruction given an input 3D point cloud. Obtaining an atlas is also useful for many applications. For example, atlas are natural texture coordinates and can be optimized by existing methods to apply new textures on 3D objects. Furthermore, we observed that each patch naturally specializes in a part of the object. We explored this idea further in a follow-up paper and obtained state-of-the-art results on human correspondences. The code is available. Thank you all for your attention, and come visit us at the poster to get the beginning.
Good morning, everyone. I'm Zhenheng Yang from University of Southern California, and here I'm presenting our work on learning age with geometry all at once by watching only videos. And our task is to unsupervisedly learn the 3D geometry. So during training, only the monocular video is used as input. And during test, a single RGB image is fed into the network, and we will produce or estimate not only the depth, but also the surface normal and the geometrical age all at once. We are motivated by previous works, such as the one in last CVPR. Joe et al. Proposed to leverage the consistency between the source view and target view. And the depth map and the camera motion are separately estimated by a depth net and motion net separately. And these two estimated information are warped to a target view, and the photometric class is served as the supervision. And further work such as Yang et al. Has proposed to leverage extra geometrical consistency, for example, the depth and normal consistency, and have achieved better results. So, but having a closer look at their results, we can see that their produced normal are actually very noisy and do not align well with the actual 3D layout. For example, the car objects boundary do not show in their depth or normals. So we propose to joint learning the geometry together with geometrical edges. And the last row shows our result. So based on the basic architecture, we have proposed a sibling output beside the depth net, which is called H-net. And the depth is estimated by the depth net, the geometrical edge is estimated by the H-net, and the camera motion is estimated from the PoseNet. We have applied several geometrical constraints to help learning. For example, for this one is to encourage that the surface normal direction should be the same on the same surface. And the second one to constrain the depth should smoothly change on the same surface. And we also applied normalization on H-map. And the last one is the same view synthesis loss as in the previous methods. And here I'm showing some depth estimation results produced by our method. Please compare to the last column. So you can see that not only our estimated values are very close to the ground truth, but also it's aligned well. It preserves the object's boundaries in our depth estimation results. And comparing the results quantitatively, whoops. Okay, here comes our table. Comparing the numbers quantitatively, adding the extra constraint, LEGO, which is our model, has outperformed the previous methods, and incorporating more training data, which we used cityscapes as extra training data, we have even more improvement. And here we compare our surface normal results with the previous methods and also ground truth. So you can see from the figure that our produced normal are very clean, gets rid of the noise, and also preserves, align well with the 3D layout. More directly, we also have evaluation on the predicted edges. The predicted edges actually align well with the object's boundary. And here I show a qualitative results of our produced depth, which is on the right top, and also geometrical edges and surface normal. The results are generated by independently apply the algorithm on each frame and link the frame into a video. So thank you, and welcome to our poster stand. Our code will be released soon. Thank you.
That concludes the session. Thank you very much, and let's quickly thank all speakers again.